So hello friends, welcome to lecture series on nonlinear programming. Now next topic is separable programming. So in this lecture we will see what separable programming is and how can we solve separable programming problems. So what separable programming is, let us see. So separable programming is one of the indirect method to solve non-linear programming problems. You see, we do not have any unique method to solve a non-linear programming problem, okay. But if we have a separable problems, objective function as well as constraints are separable. What do you mean by separable? We will discuss in this lecture. So we can solve it using separable programming, okay. It is useful in solving those non-linear programming problems in which the objective function and the constraints are separable. This method, separable programming, is used to obtain at least approximately optimal solution for a relatively large class of non-linear programming problem. In this method we are actually not finding the exact solution, but we are finding at least the approximate optimal solution of a given non-linear programming problem. We approximate the functions involved by the piecewise linear functions, that is broken straight lines. Whatever function we have given in the objective function as well as in the constraint, we approximate that functions by a number of linear functions, by number of broken straight lines, okay. Now there is no particular method to determine the number of piecewise linear functions, okay. We approximate the given function by piecewise linear functions, but we do not have any method to find the number of piecewise linear functions. Error in approximation can be reduced by having large number of linear segments. However, this will increase computational time to obtain the optimal solution. Of course, if we have larger number of linear functions, then error will be lesser. However, this will increase computational time to obtain the optimal solution. Now let us start when a function is said to be separable. Now a function involving n variables x1, x2 up to xn is said to be separable if it can be expressed as f1 x1 plus f2 x2 and so on up to fn xn, that is each fi is a function of only one variable. Suppose you have this type of function, suppose you have f x1 x2 x3 a 3 variable function, and suppose it is something like this 3x1 square plus x2 square plus 4 x3 cube, okay. So this function is clearly separable because we can write this function as f1 x1 plus f2 x2 plus f3 x3, where f1 x1 is nothing but 3x1 square, f2 x2 is nothing but x2 square, and f3 x3 is nothing but 4 x3 cube, okay. So since each function is a function of only one variable, it is of x1, it is of x2, it is of x3 only. So we say that this function f is separable, okay. Now consider this type of non-linear programming problem. It is a special case of non-linear programming problem, of course. So what we have, the objective function involved in the problem is separable, okay, and all the constraints are separable. The first constraint is also separable, second constraint, and similarly the mth constraint is separable. So such problem where the objective function as well as all constraints are separable are called separable programming problems. Now for example, we have this problem, we have maximizing fx is equals to, here it is 3x1 square plus 2x2 cube subject to the first constraint is x1 square plus x2 square less than equals to 4. The second constraint is 2x1 plus x2 less than equals to 3 and x1 x2 non-negative. So, here you can easily see that the objective function is separable because it involves, because we can easily write this as equals to f1 x1 plus f2 x2, where f1 x1 is 3x1 square and f2 x2 is 2x2 cube. Now, the first constraint is also separable because this can be written as g1 x1 plus g2 x2 less than equals to 4. Here g1 x1 is x1 square and g2 x2 is x2 square. The next constraint is also separable, it is h1 x1 plus h2 x2 less than equals to 3, where h1 x1 is 2x1 and h2 x2 is x2, and these constraints are obviously separable. So, we can say that this problem is a separable programming problem. Okay. Now, what is a separable convex programming? So, if it is a special case of separable programming in which the separable objective function, which is in minimizing form, and all separable constraint of less than equal to type are convex. So, if the involved objective function, which is of separable type, and all constraint less than equal to type are all convex, then we say that it is a convex separable programming problem. Okay. It is minimizing f is equals to, it is 9x1 square plus 5x2 square minus 5x1 plus 2x2, and subject to conditions are 2x1 square plus 3x2 square less than equal to 6, 3x1 plus 4x2 less than equal to 12, and x1 x2 non-negative. If you take this problem, so you can split f as f1 x1 plus f2 x2. You can split this as g1 x1 plus g2 x2 less than equals to 6. You can split this constraint as h1 x1 plus h2 x2 less than equals to 12. Okay. Now, what is f1? f1 is a function of x1 and it will be 9x1 square minus 5x1. These are the function of x1. So, this will come in f1. Okay. And what will be f2 x2? f2 x2 is 5x2 square plus 2x2. Now, if you take first derivative of this f1, it is 18x1 minus 5, and the second derivative of this is 18, which is positive. So, this is convex. This function is convex because the second derivative is strictly greater than 0. Okay. Now, if it is, you take first derivative of this, it is 10x2 plus 2, and the second derivative of this is 10, which is greater than 0. Again, this is convex. Okay. So, f1 f2 both are convex and the sum of two convex functions is also convex. So, this is convex. Or you can take Hessian matrix of f and it come out to be positive, semi definite or positive definite, then we can say that the function is a convex function. Now, if you take g1 x1, so g1 x1 is 2x1 square. Okay. And the second derivative of this is 4, which is positive. Again, it is convex. And similarly, g2 x2 is 3x2 square. You take the derivative, second derivative of this is simply 6, which is again positive, hence g2 is also convex. Okay. So, this constraint is a convex constraint, is a convex function, And similarly, it is a linear function, it is obviously convex, and these two are also linear. So, it is also convex. So, we say that this problem is separable as well as convex. So, we call it separable convex programming problem. Okay. So, if nonlinear programming problem, if it is a convex programming problem as well as satisfy the separability of the functions. So, we can easily say that they are separable convex programming problem. Now, come to our separable problems. Let us, to understand separable programming, let us start with a function of one variable. Okay. Now, suppose we have a function of one variable here as given in the diagram here. Okay. Now, for this curve you make this linear approximation of this function. Okay. Now, for this curve you make this linear approximation, suppose up to here, then up to here. How many grid points are there? We have 4 grid points. Suppose this is a linear approximation. So, this is A1, this is A2, this is A3, and this is A4, and this is y is equals to fx. Basically, what we have done, we have a given function of one variable as y equals to fx. We are trying to find out the linear approximation of this function. So, we have splitted the curves into finite number of broken lines, piecewise linear functions. Okay. This curve is approximated by this straight line. This curve up to here is approximated by this straight line. This curve we have approximated by this straight line. Okay. Okay. Of course, if we increase the number of, we can make 2 straight lines or we can make 3 straight lines also here if for to approximate this given curve. Okay. So, if we increase more straight lines, so complexity to find the optimal solution will increase. Okay. Here for a simplicity, I am taking only 3 linear approximation of this curve. Now, these A1, A2, A3, A4, these are called grid points. These are called grid points. Now, how to find linear approximation of this f? Let us see. Now, this point will be nothing but it is A1 f of A1. Okay. This point is A2 f of A2. This point is A3 f A3. This point is A4 f A4. Okay. Now, if x belongs to A1 to A2, this is x, okay, and this is fx or y. Okay. Now, if x belongs to x in this interval A1 to A2, so how to find y in this interval? So, this is the equation of a straight line passing through 2 points, passing through A1 f(A1) and A2 and f(A2). So, what will be the value of the function? That we can easily see, it is fx is equals to f(A1) plus f(A2) minus f(A1) upon A2 minus A1 times x minus A1. That will be the equation of a straight line passing through 2 points A1 f(A1) and A2 f(A2). Okay. So, in this way we can find the value of f at any point in between this line segment. Okay. Now, this x is in between A1 and A2. Okay. So, x is belonging to A1 and A2. This means x is a convex linear combination of these 2 points, because x is between A1 and A2. So, x will be something A1 lambda 1 A1 plus lambda 2 A2. So, where lambda 1 plus lambda 2 is 1 and lambda 1 lambda 2 are non-negative. Okay, because x is in between A1 and A2. Okay. Now, what is x minus a1 from here? This implies lambda 1 a1 plus lambda 2 a2 minus a1. So, this will give lambda 1 minus 1 times a1 plus lambda 2 a2, and lambda 1 minus 1 from here is minus lambda 2. So, this will give lambda 2 times a2 minus a1. Okay. Now, when you substitute this over here, because x minus a1 is this quantity, when you substitute it over here in this equation, a2 minus a1 will cancel from the denominator, lambda 2 will come here. So, what we obtain? We obtain f(x) is equals to f a1 plus f a2 minus f a1 into lambda 2, because this is cancelling in both the sides. Okay, from a denominator this will cancel. So, this will give, now this is 1 minus lambda 2, 1 minus lambda 2 is lambda 1. So, it is lambda 1 f a1 plus lambda 2 f a2. So, where lambda 1 plus lambda 2 is 1 and lambda 1 lambda 2 are non-negative. So, that means if x is in a convex linear combination of a1 and a2, the similarly f(x) will be the convex linear combination of f a1 and f a2, if we are talking in between a1 and a2. Now, similarly if you talk x in between a2 and a3, then f(x) will be similarly f lambda 2 f a2 plus lambda 3 f a3, where lambda 2 plus lambda 3 is 1 and lambda 2 lambda 3 are non-negative. Okay, on the same lines we can obtain if x lying in between a2 and a3. So, corresponding f(x) which is in this straight line will be the convex linear combination of f a2 and f a3. Now, here it to be noted that lambda 2 is same. What you see, when x is between a1 and a2, so f(x) we obtain as lambda 1 f a1 plus lambda 2 f a2, where lambda 1 plus lambda 2 is equals to 1 and lambda 1 lambda 2 are non-negative. So, whatever lambda 2 is here, the same lambda 2 is here. This is the important condition here. Okay. Now, similarly if x is in between a3 and a4, so what will be f(x)? If it is in between a3 and a4, so f(x) will be nothing but, now it is lambda 3 f a3 plus lambda 4 f a4, such that lambda 3 plus lambda 4 is 1 and lambda 3 lambda 4 are greater than equal to 0, and lambda 3 is same, whatever here same here. Okay. So, what will be the linear approximation of this f? Now, if you combine all the 3 terms, so the linear approximation of this f will be lambda 1 f a1 plus lambda 2 f a2 plus lambda 3 f a3 plus lambda 4 f a4 subject to lambda 1 plus lambda 2 plus lambda 3 plus lambda 4 equal to 1 and all lambda i's are non-negative. And what will be x? X will be lambda 1 a1 plus lambda 2 a2 plus lambda 3 a3 plus lambda 4 a4. And now the important condition here is at most 2 lambda i's are greater than 0 and they must be adjacent. Why this? Let us see. You see, either we have to minimize or we have to maximize a given objective function. Okay. Now, for this particular function, if we say this, for this particular function, it will attain, suppose we are taking a minimization problem, okay. It will attain minimization on one of the line segment, okay. We have approximate this given curve by a finite number of piecewise linear functions, okay. If it is a minimization problem, so it will attain minimum at one of the linear function, okay. Suppose here it is minimum, suppose for this function here it is minimum. So, it will attain minimum, if it is attaining minimum over here. So, this linear straight line will approximate this optimal solution, okay. Not the entire all the straight lines, only that straight line is important, which where we are obtaining the minima, okay. Now, if this is a straight line which is giving an approximate optimal solution for this particular problem, then only lambda 3 and lambda 4 are important, I mean greater than 0, those are consecutive and all others are 0. That is why at most 2 lambda i's are must be greater than 0 and they must be adjacent, okay. Either these two or these two or these two. If it is optimal over here, only lambda 3 and lambda 4 are important. They are adjacent, lambda 3 and lambda 4, and they must be positive. All others must be 0 in that case, okay. So, whenever we have a separate programming problem and we are taking respect to a variable, say x1, a one variable function, so then we are approximating functions by number of linear functions, okay, piecewise linear functions. So, in that with respect to that variable, only 2 lambdas must be greater than 0 and they must be adjacent, okay. So, in this way we can find out a linear approximation of a given function f. So, all this description are over here in the slides, okay. So, the expression 5 gives piecewise, this is expression 5. So, this gives piecewise linear approximation of f(x) in the interval a1 to a4. Here the points a1, a2, a3, a4 are called grid points, okay. Suppose we have this function, okay. Now, this function is also of only of one variable. So, f(x) is equals to x1 cube minus 3x1 square plus 4x1 plus 3, okay, plus 2, and subject to conditions are 0 less than equals to x1 less than equals to 3. Now, suppose this function is a function of only one variable x1 and we want to find out linear approximation of this function. How to find? So, this is the bound of x1, x1 must be greater than equal to 0 and less than equal to 3. So, first we find out the grid points, finding grid points is in our hand, okay. So, we take grid points like this, it is 0 and it is 3. You see x1 is between 0 and 3, it is 0, it is 3, okay. So, we can divide grid points as 1 and 2. So, it is one grid point 0, 1, 2, 3, these are grid points. We can take grid point as half also, 3 by 2 also, I mean 3 by 2 also, but it will make the calculation difficult, okay. For convenience we take grid points as 0, 1, 2, 3, okay. We can increase the grid points also, no problem, okay. So, for convenience we are taking only these grid points 0, 1, 2, 3, okay. Now, first grid point a0 is 0, a1 is 1, a2 is 2 and a3 is 3. So, what is fa0 then? fa0 you substitute it over here, so it will be 2. What is fa1? fa1 is here, you can simply see it is 6 plus 1 7, 7 minus 3 is 4. And what is fa2? fa2 is you substitute a2 x is equal x1 equal to 2. So, when you substitute x1 equal to 2, it is 8, 8 plus 2 10, 10 10 plus 8 is 18, 18 minus 12 is 6, and FA3 is 14. So, these are the values we obtain. Okay. So, what will be a linear approximation of this f? Nothing but it is suppose it is lambda naught over here, lambda 1 here, lambda 2 here, lambda 3 here. So, it is 2 lambda naught plus 4 lambda 1 plus 6 lambda 2 plus 14 lambda 3. It is lambda naught f a naught plus lambda 1 f a 1 plus lambda 2 f a 2 plus lambda 3 f a 3. So, 2 into f a naught lambda naught, 4 into lambda 1, 6 into lambda 2, 40 into lambda 3, subject to lambda naught plus lambda 1 plus lambda 2 plus lambda 3 must be 1. All lambda i's must be greater than or equal to 0, and at most 2 lambda i's are greater than 0 and they must be adjacent. Okay. And what will be x, the x1, the optimal solution? X1 will be 0 into lambda naught plus 1 into lambda 1 plus 2 into lambda 2 plus 3 into lambda 3. So, that will be the optimal solution, 0 into lambda naught, 1 into lambda 1, 2 into lambda 2, 3 into lambda 3. So, this is how we can find out linear approximation of a given function f. Okay. So, thank you.